This video is about ideals and factor rings. We begin with ideals, and we begin with definition of an ideal. A subring A of a ring R, so if we have a ring here and a subring here, is called a two-sided. It can be one side, but here we are going to show only two-sided. A two-sided ideal of the ring R if for every R in, this is a ring. I'm addicted to write real numbers, so okay, so for every R, element R in the ring, and every A in the subring, so R will be here and A will be here. For every R in the ring and every A in the subring, both RA and AR are in A. So if you, I'm going to call this, so this is subring A, okay, and A times R will be here, and R times A will be here. So it absorbs the products, okay. So when you do the product, okay, both products, AR and RA, they both are in the subring A. If this happens, we say that A is an ideal of the ring. So this subring is a particular subring, is a ideal of the ring. This ideal A, ideal of the ring, is called a proper ideal of A. A proper ideal A, a proper ideal of the ring, if A is a proper subset of the ring. So A should be a proper subset of the ring. Okay, and now it is we get into the usual question: how do I identify ideals? If I have a subring, how can I identify an ideal? So we have a, let us call it a ideal test. Okay, so this is the ideal test. A non-empty subset A of a ring R is an ideal. So we have a ring here, and here we have a subset that should be a subring, okay. So this subring will be an ideal if for all elements A and B in A, if A minus B, the element A minus B is here. And for all R, we pick an element R in the ring and an element A in the subring. RA and AR are both in the subring. So for all elements in the subring, if the subtraction is in the subring, and if the product of an element, so if it absorbs products or absorbs elements, if the product of an element from the subring times an element in the ring is in the subring, so A will be an ideal. Okay, so the first example is for any ring. I'm going to call the ring R. the subring, the set of the null element, and the ring, these two are ideals of the ring R. This ring, the set with the element 0, is called the trivial ideal. Another example is n times the integers, nz, the set of 0 plus and minus n plus and minus 2n, is an ideal of the integers. So, for instance, the even integers is clearly an ideal of the integers. Now, a third example will be if we have a ring, a commutative ring with unity, and we have an element in the ring. The set generated by A, so it will be the set RA, such that R is in the ring. Okay, is an ideal of the ring, and this one is called the principal ideal generated by A. Of course, this is the same notation for a group, a cyclic subgroup generated by an element, right? It's the same. But here, same notation, but here means something different. The principal ideal generated by A. Of course, the context will show the difference, okay? Another example is this, the set of full polynomials with real coefficients, okay? And A will be a subset with polynomials with constant term 0. So it will be, for instance, the polynomial x squared plus x plus 0, and the polynomial 2x plus 0, okay? The polynomial, so the constant term will always be 0. This set, this subset A, is an ideal of the polynomials with real coefficients. Now, you can check as a last example. Let us think of the ring of all real valued functions of a real variable, okay? And think of a subset S of all differentiable functions, okay? S will be a subring of this ring, but S will not be an ideal. You can check that. Here we open a new chapter on factor rings. So we think of a ring R and A, an ideal of this ring. This ring is a group under addition because we have a ring, addition, multiplication, right? So the ring is a group under addition. So the group and addition, this is a group, actually should be even a commutative group or an abelian group. It's a group under addition, and A is a normal subgroup. So a normal subgroup is one where the cosets, the left cosets, are equal to the right cosets. Okay, so A will be a normal subgroup. So A will be a normal subgroup of R. So we may form a factor group or a quotient group where to the normal subgroup we add R elements such that R is in the ring. Okay, so this is the factor group of the ring by a normal subgroup. Okay, now the question is, it's like in the groups, right? The idea is more or less the same. How many of these can we form? A plus the ideal, B plus the ideal, AB plus the ideal. Okay, so how many can we form? So we get into the next theorem. So we get into the next theorem that says it's about the existence of factorings. Let R be a ring and A a subring of ring R. The set of cosets R plus A such that R is in A. So R is in A. No, there is a mistake here. R plus A, R is in the ring. I'm sorry for this. Okay, the set of cosets such that, so A is the subring, okay, plus R, R an element in a ring, of course, is a ring under the operations S plus A plus T plus A equals S plus T plus A, and S plus A times T plus A equals ST plus A. So this cosets under this operation will be a ring if and only if A, the subring, is an ideal of the ring. Okay, so this A, if this A, this subring of the ring, if this A is an ideal, so the set of these cosets will be a ring under these operations. Okay, I'm not doing the proof here. It takes some time, but it's really easy. So I show you here a quick example of these factor rings. So we have the factor of the integers by the multiples of 4, and as we said before, this is an ideal. The multiples of 4 are ideals of the integers. So the factor ring Z by the multiples of 4 is a set of Z plus 4, the multiples of 4, 1 plus the multiples, this is a Z, 2 plus the multiples of 4, and 3 plus the multiples of 4. Of course, 4 plus the multiples of 4 will be 0 plus the multiples of 4. Let us pick two elements, 2 plus the multiples of 4 and 3 plus 4z, and let us do the operation addition and multiplication. How is addition? 2 plus 4z plus 3 plus 4z. So that will be 2 plus 3, that's 5, and this is multiples of 4. So 5 will be 1 plus 4 plus 4 of z, but this one we saw here is like 0. So at the end, adding these two numbers is like 1 plus 4z. What about the multiplication? So 2 times 3 is 6, and here we have 4z, right? So 6 is like 2 plus 4. 4 again is like 0, because it's module 4. So this product is this. You have another factor group here, the multiples of 2 by the multiples of 6, and that will be, sometimes it's a bit hard to see this, but it will be 0 plus 6z, 2 plus 6z, and 4 plus 6z. Okay, so here essentially the operations will be module 6. Okay, so you can see, you can check that this factor ring is isomorphic to C3. Okay, and here we have a last example. We have the ring of polynomials with real coefficients and x squared plus 1, the principal ideal generated by x squared plus 1. So this ideal will be x squared plus 1 will be x squared plus 1 times the polynomials f of x, such that f of x are in the ring of polynomials with real coefficients. So the factor ring of the reals by this principal ideal, the factor ring of the this is wrong here. I'm sorry, one sec. This is wrong, because this should be Rx, right? The polynomials. Okay, so the factor group of the ring of polynomials by the principal ideal generated by x squared plus 1. That will be the set of x squared plus 1. Of course, this is wrong too. I'm sorry, because it's not sufficiently clear that this is the ideal generated by this x squared plus 1 plus all the polynomials. Okay, so that will be the polynomials plus the ideal, where a and b, so this the coefficients of the polynomials, will be in the reals. And probably if you are following very closely, you're quite surprised for the fact that gx is ax plus b. You can say, how can that be? Because we have so many polynomials, right? Like x cubed plus x squared, and with this ideal, how come this set, where this would be g of x, this polynomial. How come this set is this set? That's a very good question. So gx, this one, will be a member of the ring of polynomials with real coefficients. Okay? So we can write this. I'm going to write this polynomial as q of x times x squared plus 1, right? The ideal. Plus rx. So q plus rx. This q will be the quotient, and r will be the usual, the remainder. The remainder of dividing, when I divide g of x by x squared plus 1. When I perform this division, I will get q of x, and of course I will have a remainder, r of x. Okay? So yes, so I can say that g of x is q of x, the quotient, times the divisor plus the remainder. Okay. In particular, if the remainder is 0, or if the remainder has degree less than 2, meaning r of x is ax plus b for some a and b in the reals, right? So we will have g of x plus the ideal equals q of x, right? Q of x times x squared plus 1 plus the remainder plus, yes, plus, because all this is g, so plus the ideal. Okay, so that will be the remainder plus x squared plus 1, sorry, x squared plus 1, the ideal generated by x squared plus 1. Oh, this is really ugly, this r of x. Okay, so that will be the remainder plus this, right? But now, since the ideal, this ideal here, absorbs this term, because the ideal is going to absorb the term, how are we going to do the multiplication? Okay, so the multiplication will be, for instance, x squared plus 1 plus the ideal will be this x squared plus 1. It will be absorbed, so it will be 0 plus x squared plus 1. So one has to think of this like 0, okay? Or if you prefer, think this way. Oh, sorry. If you prefer, think this way. I can give a quick example here. For instance, x plus 3 plus the ideal, I close it here, times 2x plus 5 plus the ideal. Okay, so x times 2x, that will be 2x squared plus 11x plus 15 plus the ideal, of course. But if you look well, this one will be 0. So you will have 11x plus and through this ideal, this will not 15 will be 13, right, plus x squared plus 1. Okay, so the funny thing is that you end up having ax plus b plus x squared plus 1 generated by x squared plus 1. Okay, where for instance x squared plus x squared plus 1 equals minus 1 plus x squared plus 1. Okay, and the surprising fact is that this is going to be isomorphic to the complex numbers. Okay, I'm sorry, this I'm better to put the ring here. So this ring x squared plus 1 is isomorphic to the complex numbers.